Okay, this is section 10.3. We're still talking about probability. This is found on page 414 in your textbook if you're following along. And if you'll recall in the last section, finding the probability of an event, we said was the number of favorable outcomes over the number of all possible outcomes. So for instance, if you were rolling a die and you wanted a 3, well, there's one way a 3 could show up, so that would be the number of favorable outcomes. But there are 6 possible things that can happen when you roll a die. So 1 out of 6 chance of rolling a 3. If you just wanted to roll something less than a 6, well, then the number of favorable outcomes would be 5, because there's a 1, a 2, a 3, a 4, and a 5. All 5 of those are less than 6. And the total number of possible outcomes would still be 6, because there are still 6 possible things that could happen. Well, in today's lesson, we're talking about 2 different types of probability. The first one is called experimental probability. Experimental probability is what we get when we actually run the experiment. And remember, for math, running an experiment could be as simple as flipping a coin or rolling a number cube. So to find the experimental probability, we take the total number of times our event occurred over the total number of trials. So let's say we wanted the experimental probability of flipping heads. If we flipped a coin 10 times and we got heads twice, then we would put 2 over 10. Heads occurred 2 times out of the 10 times we flipped the coin. We would expect it to be 5 out of 10 because we know the probability of flipping heads is 1 out of 2 or 50% of the time, but we know from reality that when we flip a coin 2 times, we don't always get 1 heads, 1 tails. In fact, we could flip heads many, many times in a row or none for a while because we're getting tails many times in a row. We know that's reality. So for experimental probability means we are actually running the experiment. So that's an easy way to remember. That's experimental probability. Let's look at their first example. Now, they're not actually going to make us roll the number cube. They've already rolled the number cube for us, and they graphed right here in this table here how many times they rolled each number. So this means, well, there are 6 different numbers they could roll, obviously, because it's a number cube. And they rolled a 1 10 times. They rolled a 2 4 times, a 3 8 times, a 4 11 times, a 5 11 times, and a 6 6 times. So they did not roll all of the numbers evenly, and we do need to figure out how many times they rolled the number cube. That's very important because that'll be the denominator of our experimental probability. Now you could go over here and count all these up. Here are 10 plus 4 plus 8 plus 11 plus 11 plus 6. If we add all those up, we get 50. Or I could just look over here and it says the bar graph shows the results of rolling a number cube 50 times. So it tells us they rolled it 50 times. So when we're going to write this experimental probability, we know that 50 will be our denominator because that's how many times we ran the experiment, or the total number of trials. So now let's look what their question is. What is the experimental probability of rolling an odd number? So a 1, a 3, or a 5. Well, we rolled a 1 10 times. We rolled a 3 8 times. And we rolled a 5 11 times. So when we rolled this number cube 50 times, we got an odd number 29 of the times. So the experimental probability of rolling an odd number is 29 out of 50. That's different than the probability we would have just calculated, because we would have said 3 out of 6, or 1/2 of the time we should have rolled an odd number. And in reality, we rolled it 29 out of 50. So this is experimental probability. We get it by actually running the experiment. Now, sometimes we use this to make a prediction. Here's one. It rains 2 out of the last 12 days in March. So it rains 2 out of the last 12 days of March. If this trend continues, how many rainy days would we expect in April? Now we know that actually weather doesn't continue predictably like that, especially here in northern Michigan. However, we are going to play along and use this experimental probability because this is what actually happened. So 12 days went by, and out of that, 2 of those days it rained. So the probability of rain equals 2 out of 12, which simplifies to 1 out of 6. So experimentally, or because this actually happened, 1 out of 6 of the days it rained. Now, if this trend continues, how many days will it rain in April? April has 30 days in it. So if 1 out of 6 of the days it rains, what would that be out of 30? So 1 out of 6 equals how many out of 30? And now we're back to our proportions like we've been doing all year. 6 times 5 is how we get 30. 1 times 5 is 5. So we would expect it to rain 5 days in April. Okay? So using March's data from the last 12 days of March, we would expect 5 days of rain in April, which is probably not too realistic. In fact, it is raining today. Here we go, on your own. Number 1. In example 1, what is the experimental probability of rolling an even number? Well, this is kind of an easy one because, for example 1, remember we rolled the number cube 50 times, and 29 of those times it was odd. Well, if 29 of the times it was odd, how many of the times was it even? The other 21 times, because 29 plus 21 equals 50. So it says, what is the experimental probability of rolling an even number? So probability even, 21 out of 50. So this was number 1 for on your own. 21 out of 50. For number 2, at a clothing company, an inspector finds 5 defective pair of jeans in a shipment of 200. And I'm not sure what a defective pair of jeans would look like. Maybe like one pant leg is missing, or the zipper's on the back, or the pockets are sewn shut. I have no idea. But at this clothing company, an inspector comes in, and out of 200 pair of pants that inspector looks at, she finds 5 defective pair of jeans. If this trend continues, about how many pairs of jeans would you expect to be defective in a shipment of 5,000? So let's look. 5 out of the, we'll put it down here. 5 out of 200, so that was the probability of defective. 5 out of 200, which simplifies to 1 out of 40. So 1 out of 40 was defective. We want to know how many out of 5,000. So what would that equal if the total wasn't 40 anymore, but was 5,000? So again, we're using our proportion. And 40 times what is 5,000? I have no idea, but I can figure it out with a little division. 5,000 divided by 40. 40 goes into 50 once. 40 goes into 100 twice. And 40 goes into 200 5 times. 125. We can expect 125 defective pair of jeans. That was for number 2 for on your own. Well, that brings us to the next key idea. It's a different type of probability. This is theoretical probability. This is what we're used to. It's what in theory should happen. For instance, if we flip a coin 10 times, we should get 5 heads and 5 tails. We know that may or may not be the actual case, but theoretically, that is what should happen. So when we find theoretical probability, that's when all possible outcomes are equally likely. The theoretical probability of an event is how the number of favorable outcomes over the total number of possible outcomes, like we did in the last section. Not earlier this lesson, but in the last lesson. So now we've had experimental probability. That's what we did just a couple of problems ago. And here we're doing theoretical probability. So find the theoretical probability. You randomly choose one of the letters shown. What is the theoretical probability of choosing a vowel? Well, 1, 2, 3, 4, 5, 6, 7. So for example, number 3, we know the denominator will be 7 because there's 7 total things we could choose, all 7 of these. Now, how many of those are vowels? Well, the E is a vowel, the O is a vowel, and the other E is a vowel. So there are 3 chances for us to pick a vowel out of those 7. Theoretically, there's a 3 out of 7 chance of picking a vowel. Using theoretical probability. So what's the theoretical probability of winning a bobblehead when spinning a prize wheel is 1 out of 6. The wheel has 3 bobblehead sections. How many sections are on the wheel? So here they have simplified the probability to get 1 over 6, and they're telling us there's actually 3 bobbleheads. So for example 4, try to squeeze it in down here. Example 4, we know that the probability simplifies to 1 out of 6. But they're telling us there are 3 bobbleheads. So we know there are actually 3 bobbleheads. How many total spaces on the wheel? Again, using proportions. We multiply the top by 3 to go from 1 to 3, so we multiply the bottom by 3 to get 18. And let's see if that makes sense. If there are 18 total places, and 3 of them are bobbleheads, then we'd have a 3 out of 18 chance, which does simplify to 1 out of 6. So yes, 18 spaces on the wheel. For the on your own here, number 3, it says, in example 3, what is the theoretical probability of choosing an X? Well, remember that in number 3, they had the letters for explore. 1, 2, 3, 4, 5, 6, 7. Yep, 7 letters. And what's the theoretical probability of choosing an X? There's only one X. So 1 out of 7 chance of choosing the X. What about number 4? The theoretical probability of spinning an odd number on a spinner is 0.6. The spinner has 10 sections. How many sections have odd numbers? Well, .6 is the same as 6/10. So for number 4, they're telling us the probability of an odd number is 6 out of 10. And then the spinner does indeed have 10 sections. Well, that's easy. How many are odd? Ding! 6 of them, because 6/10 is our chance of getting an odd. So 6 out of 10 are odd. Finally, number 5. The prize wheel in example 4 was spun 540 times at a baseball game. About how many bobbleheads would you expect were won? So we have to go to example 4. What you remember, if we're looking at example 4, was this where 1/6 was the probability of getting a bobblehead? 1 out of 6. So now let's go back to this problem. If we're using that 1 out of 6, 1 bobblehead out of 6 spins, how many bobbleheads would we expect out of 540 spins? Well, we have to multiply the bottom by 90. So we multiply the top by 90. And we get 1 times 90 is 90. 90 bobbleheads. Now, that's the theoretical probability. Does that mean for sure we would give away 90 bobbleheads? No. It's possible we give away 540. What if somebody just kept on spinning that bobblehead space? Also possible we give away 0. Could just be an unlucky day for the fan spinning the wheel. But theoretically, we would expect to give away 90 bobbleheads, and they asked us for theoretical. Finally, comparing experimental and theoretical probability. So if we look here they rolled a number cube. They rolled it how many times? 300 times they rolled this number cube. And they got 1 48 times, 2 53 times, 3 50 times, 4 52 times, 5 49 times, and 6 48 times. If they rolled it 300 times, we would expect to get 50 of each. Okay, 50 of each, because there are 6 possible things when you roll a number cube, 6 possible outcomes, and each one of these numbers is one of them. So we expect to get it a 1 out of 6 times. We expect to get a 2 1 out of 6 times, a 3 1 out of 6 times, and so on. If we roll it 300 times, we multiply by 50 on the bottom, we multiply by 50 on the top to get 50. We don't actually get 50, but these are pretty close. In fact, the number 3 we've rolled exactly 50 times. So that's the only one that showed up exactly how we would theoretically think it was supposed to. The more we run an experiment, the greater number the trials, the closer our experimental probability will get to our theoretical probability. Okay, so the more trials we run, the closer theoretical and experimental probability will get. I won't ask you that on a quiz or anything, but you should probably know that. Okay. Let's do just a couple of these practice problems off of page 417. Using the bar graph to find experimental probability. So we're using their data here to figure out experimental probability. The first thing we need to know, because it doesn't tell us, how many times did they spin this spinner? Well, they spun a 1, 2, 3, 4, 5, and a 6, and they spun a 1 8 times, a 2 6 times, a 3 9 times, a 4 11 times, a 5 9 times, and a 6 7 times. So we have to add 8 and 6 and 9 and 11 and 9 again and 7. And if we add all those up, what's that? 20, 29, 36, 42, 50 times. They spun this spinner 50 times, and I got that by adding up all of the results. What's the experimental probability of spinning a number less than 3? Well, now we know that our denominator will be 50 because that's how many times they ran the experiment. So our denominator for number 8 will be 50. And we have to find out spinning a number less than 3. So they spun a 1 8 times, a 2 6 times, and 3 is not less than 3. So we just have to add up 6 and 8 to get 14. And if you want, you can simplify that to 7 over 25. Number 9. It's not spinning a 1. Well, they spun this thing 50 times, so we know that's our denominator. And if they spun a 1 8 times, I know the other 42 times are these over here. I don't feel like adding those up. They must add to 42. So 42 out of 50, which is the same as 21 out of 25. Number 10. Spinning a 1 or a 3. So now we add the 1 and the 3 up. We have 9 here and 8 here. That gives us 17 out of those 50 spins. And finally, spinning a 7. And how many times did they spin a 7? None. So I didn't say there are no 7s. I'm just saying they didn't spin a 7. I don't actually know what this spinner looks like, but they have not yet spun the number 7. So for number 11, we would put 0 out of 50, which is the same as just 0. Let's look at number 13 down here. Here's a board game. It says there are 105 lettered tiles in a board game. You choose these tiles, shown. How many of the 105 tiles would you expect to be vowels? So you took a little sample of the tiles. You didn't feel like looking at all 105 of them. You picked these 7. And out of those 7, so 7, this is number 13. Out of those 7, so 7 is the denominator. You pulled 7 of these out. 1, 2, 3 of them are vowels. The E, the A, and the I. So 3 out of 7 were vowels. You want to know how many could you expect out of the 105? Now, it's quite possible that all of the rest, it's not quite possible, but it is possible that all of the rest are vowels or none of the rest are vowels. Maybe you got all of the vowels in your first try. But using the data we have, if we're going to extrapolate this or use it to show us a bigger amount, we would take our 3 out of 7 and multiply the bottom by 15 to get 105. Multiply the top by 15. 3 times 15 is 45. We would expect 45 vowels out of the 105. Excellent. Well, head over to the other video to do the homework, which is journal page 220, lesson 10.3.